I'll continue today with an investigation of rotational analogs. And that's been the whole story along, getting quite tired of hearing me say it, but I started out with analogs to rotational kinematics, where I replaced displacement, velocity, and acceleration with angular displacement, angular velocity, and angular acceleration. When I recognize an angular acceleration, the next thing to do, of course, is to ask the question, how is it that I produce an angular acceleration? The answer to that is torque. Torque is the rotational analog of force. And along the way, I have the rotational analog of mass, which is the rotational inertia. I have the rotational analog of kinetic energy. I even wrote a rotational analog of the work energy theorem. That is, the work done by a torque is the torque multiplied by the angular displacement. So, as I would have said in the introduction, everything that we've done so far in classical mechanics is revisited in the context of rotation. Well, consider Newton's second law written in our sort of preferred form, that the net force that acts on an object is equal to the rate of change of its momentum. The momentum of vector quantity, here I write in terms of the derivative dp dt, the momentum of vector quantity, and it's the rate of change of that momentum, the quantity of motion, that is equal to the force. Naturally, the momentum has contained in it both concepts of the velocity, because it's defined in terms of the velocity, and the inertia. And so I found that the momentum to be a very, very useful quantity for solving all kinds of physical problems, particularly problems where two systems interacted the one with the other, interactions that we call collisions. And I discovered that fundamentally there's a law at work underneath called the law of conservation of momentum. So this is my translational law in the context of a momentum here, vector p, that is the mass times the velocity. We see that the momentum gets its vectorness from the velocity, which is, of course, a vector multiplied by the scalar mass. You have to wonder if there's a rotational analog of momentum. And indeed there is. In order to define it, I'll simply replace all of my translational quantities with their associated angular quantities. So naturally the mass I'll replace with the moment of inertia. The moment of inertia, generally ml squared, or mr squared, pardon me, with some fractions involved depending on the way the mass is distributed in space, is a scalar quantity. It's just a number that I can calculate that represents the resistance of an object to rotational motion. And then I'll multiply that by the rotational analog of velocity, which of course is the angular velocity, and I've created a quantity that I've never seen before. I times omega. I times omega, the rotational analog of momentum. It needs a symbol, and that symbol is capital L. Capital L, the angular momentum. Once again, I've revealed in my classical mechanics a physical quantity that's absolutely critical to our understanding of the universe in a classical sense, but also this quantity, the angular momentum, has a much deeper mystery to it. Actually, there's more going on here than you'll realize even when we're done going through this basic introduction of angular momentum. It turns out that angular momentum is a more subtle quantity and important to the sort of foundations of the universe, if I can be that dramatic. Notice that when I wrote the angular momentum, I did not put a harpoon on the angular momentum. Angular momentum is a vector. We'll find that in just a moment. Angular momentum is a vector quantity, but it's not a vector quantity defined this way. What I've written here with this analogous expression is the magnitude of the angular momentum. It must be, because the moment of inertia is a scalar and the angular velocity is a scalar. By definition, a scalar. So this gets me the magnitude of the angular momentum, and you might not be surprised to learn that since the rotation of objects can be described as clockwise and counterclockwise, positive and negative according to my choosing, I, as a practical matter going forward, will likely only use the magnitude of the angular momentum and figure out the direction on my own. Nevertheless, I need a definition of angular momentum that has this vectorness to it, which I'll come to in a moment because I've realized just now that I have an opportunity here with the angular momentum to define its units, and I should do that. Since the angular momentum has units of moment of inertia, well, what would they be? Every moment of inertia is in some way mr squared. So that's going to be kilograms and then meters squared in the moment of inertia. And then omega has units of 1/seconds, of course, is the unit that I have there. So I want to put this together. There is no more fundamental unit for this. Obviously, this is going to be a kilogram meter squared per second. And I might look at that and wonder, how am I going to make that more fundamental? I don't see any way that I make that easier to look at or easier to handle. So kilogram meters squared per second is my unit of angular momentum that at least I'm going to use for the time being. By the way, now that I have the angular momentum, you might wonder, is there a rotational analog for Newton's second law that appreciates the angular momentum? And now I can write it in here under my original Newton's second law. Whereas I would write the net torque is equal to the moment of inertia times the angular acceleration, I may also write that the net torque is equal to the derivative of the angular momentum with respect to time. Whereas the translational force is the rate of change of momentum. The net torque is the rate of change of the angular momentum. And so I have this completely analogous behavior between these two pictures. But I want to point out a thing, is in the case where the net external force, that is where sigma F is equal to 0, which is a case that I encounter sometimes, in collisions where there are only internal forces acting, I know that all of those internal forces are action-reaction pairs, so they add to 0. And if there are no forces from outside the system acting on it, then the net force, sigma F, is equal to 0, and the consequence of that is that the change in momentum vector must be equal to 0. That is the simplest way, I think, of stating the law of conservation of momentum. That in the absence of external forces, that the change in the momentum vector would be equal to 0. I can write similarly here by analogy that if the net torque, is equal to 0. That is, I have some system perhaps that has many parts, an Atwood's machine, for example, where there are many moving parts in the system and they exert forces one upon the other. Those forces are always action-reaction. And so torques, in an analogous way, internal to the system are action-reaction. For every torque, there's a counter-torque, an equal and opposite counter-torque. Therefore, all of the torques internal to a system sum to 0, guaranteed, as a consequence of Newton's third law. But there can be external torques exerted on a system. Imagine that there's some apparatus here with moving parts going around in circular motion. I look at it and I observe all of the torques associated with the tensions in ropes or the forces of gears acting one upon the other. That's fine. But then I come and I exert a force on it externally. So we use the palm of my hand and rub it against one of the wheels. Now there's an external friction force that exerts an external torque on the system. But what I'm asserting here when I say sigma torque is equal to 0, that external torques are in fact equal to 0. A consequence of that immediately, that I'm mature enough now to understand, context of my physics, is that there must be a law of conservation of angular momentum. And indeed there is. A law of conservation of angular momentum that in the absence of external torques I can use as leverage and rely upon to solve physical problems. So that's my analogy that gets me the angular momentum, and the thing that I have to deal with now is the fact that the angular momentum is actually a vector. I need a vector definition of the angular momentum, and that vector definition has a few features that as a student of physics you're going to want to pay careful attention to, because it will help you solve problems and have an effect on how you plan solutions to some of the trickier problems that we're going to do. So here I go with my definition. I'm going to say something that you might find somewhat surprising. According to our definition, which I haven't stated yet, but it's moments away, according to our definition of angular momentum, an object traveling through space in a straight line, may actually be defined to have a quantity of angular momentum. And that's kind of a strange thing. If I say angular, you think about things going around in circular motion. But an object traveling in a straight line may, by definition, have angular momentum. So let me consider my definition in that context. Here I have a straight line in space, straight as I can draw. Do the best that I can. Here I have a straight line in space, and somewhere along this line, I have an object of mass m, presumably, that's moving along this way. Oh, gee, not very good. Hang on, moving along this way, and I'll draw a vector. So the vector indicates it's moving along the line. It's the worst vector I've ever drawn. It's the worst vector I've ever drawn. It's so bad, I'm willing to accept the delay as I redraw the entire diagram from scratch. Here I go. So trying to get my straight line there. And now here is an object that is moving along, and it's just never going to get better. It's never going to get better, so I'm just going to live with it. Oh my gosh. Oh my gosh. This is like, it's just going to, apparently it's just going to point downward a little bit. I'm hoping that there are people in the audience who are like, that's fine. Why are you so obsessed with it? Okay. I've drawn a vector. I'm not labeling it velocity. I'm going to label it momentum, because this object has a mass m and a velocity v such that it has momentum. The vectorness of momentum comes from the vectorness of the velocity, and naturally the velocity vector points along the trajectory, which is a straight line. When I define the moment of inertia, I choose an axis of rotation. When I define angular velocity, angular displacement, angular acceleration, all of these angular quantities, there's an axis of rotation which is defined. So I'm going to define an axis of rotation in space here. But my axis of rotation is going to be down here on this other line that I draw parallel. So see, I have two parallel lines here. And I'll draw here, I guess I'll just put a big X. That is the axis of rotation. That is an arbitrary point chosen in space. Arbitrary. But don't fear it. It's arbitrary in the same way that a coordinate system is arbitrary for solving a problem. I choose the origin of my coordinate system. And when I say I'm choosing the axis of rotation, that's exactly what I'm doing. I'm choosing the origin of the coordinate system. I'm going to draw now something that's a bit familiar to us, which is the moment arm, a vector r that points from the axis of rotation, here the origin of my coordinate system, to the point at which the particle is here moving along in a straight line with a momentum p. It was in fact the position vector that describes the position of the object in space. Now, this bottom line here on which the origin of my coordinate system is, let's imagine that that's the x-axis, and I can draw for you here an angle theta, which is the angle between the position vector and the horizontal located there. And so with the magnitude of that position vector and the angle, I've now defined the position of the object in space in the instant that I've shown it here. Now, my definition of angular momentum. The definition of angular momentum is L as a vector. Now, I put a harpoon on because it's a vector definition. Definition! I'm not doing a derivation here. I'm telling you, this is how angular momentum is defined. But the angular momentum is defined as the r vector crossed into the momentum vector. And perhaps that is not a surprise, because the torque is defined as r cross f. And since the derivative of the momentum with respect to time is the force, the derivative of the angular momentum with respect to time is the angular momentum. Well, then this is not surprising that it would be defined in a similar way to torque, that it would be r cross. So since it's r cross p, I can break this down for a little practical value of the thing. R cross p is, by definition, the magnitude of r times the magnitude of the momentum times the sine of the angle between them. Now that's a little bit tricky, because when I say the angle between r and the momentum, I'm talking about, I have to make a little alteration to how I've drawn my diagram here, just so that I can draw a line here that extends out past r. That is the angle theta. So imagine that I translate the r vector along that line so that I can discover, once they're tail to tail, and of course the definition of vectors has nothing to do with where their tail sits. So as long as I keep the magnitude of the r vector the same and keep its direction in space the same, I can move it anywhere I want. So imagine I animate this and I grab hold of the r vector and I slide it along. So its tail is coincident with the tail of the momentum vector here. Then I see that the angle theta between the r vector and the horizontal is also the angle between r and the momentum vector. And so that theta is the theta that appears in the diagram. When I write the cross product this way, as the magnitude of r times the magnitude of p times the sine of the angle between them, I do not get the angular momentum, but I instead get its magnitude. You see, because this is a scalar, and the sine of theta is a scalar, and so the whole result is a scalar. I get the magnitude of the angular momentum vector. So then I'll just write that as L without the harpoon, so I don't need too much notation there. L is equal to, I'm just going to make a little alteration here in the order in which these terms appear. I'm not going to do anything mathematical, except to say the momentum times r times the sine of theta. Well, geometrically, r times the sine of theta means something in my diagram. Here is the vector r, and because I'm using the sine of theta, the dimension, the physical dimension that I get is this vertical distance between the two parallel lines that I drew. One is, in principle, the x-axis. It goes through the origin of my coordinate system. And the other is the line along which this particle with momentum p moves. This distance between the two that I'm calling a is obviously what r sine theta is equal to. So this is the momentum times a. And I'm going to make a little note here on the side that a, where am I going to make the note? I'm going to make it over here. That a gets a special name. You will not see this name in your textbook. And you may actually have to go some distance through the internet before you see this name, but this is the name that physicists actually use for this distance. And it's called the impact parameter. The reason why it's called the impact parameter is, imagine that Jules here is the target. I'm going to shoot, I have some very heavy ions, and I'm going to shoot them at Jules. If I shoot them straight at Jules, then the impact parameter is 0. If I shoot them sort of offline so that I get a glancing collision, the distance between the line that I shoot them and the line that goes straight through Jules, that's called the impact parameter. So by adjusting that, I'm determining how glancing the impact is. So as the impact parameter is a, it's a, the perpendicular distance between these two lines. And so, since I know that this is, as I generalize this more and more, well, actually, no, it's the opposite of that. Since I specify this more and more, my statement's getting a little bit more practical. The angular momentum of this thing is mv times a. mv times a. That's a very practical result that you're going to see in your problem solving. The angular momentum is mv times a. Momentum multiplied by the impact parameter, which is the perpendicular distance. This has a feature that I want to make clear to you in just a moment. Blake.
Is there any difference in the a between the impact, like how you specify a and acceleration?
Oh, no. It's lowercase a, has nothing to do with acceleration. I've just used a.
It's like, what if you have like acceleration in the same problem? Is there a sign or anything that you use to like differentiate?
I don't imagine that I would have much translational acceleration. I mean, sometimes I'll use b for impact parameter, right? So I can use any symbol that I like for impact parameter. And as a matter of fact, I have a tendency personally to use b. But I've been sort of forced by our physics and the way our physics questions tend to be asked to go with a. It's not my own preference, but you can use anything that you like. If you'd like to make up your own symbol, as long as it's clear what you're doing, we're totally fine. So I want to point out a feature that the impact parameter has. No matter what the position of this particle is, imagine, back this up so it's all the way over here on the left-hand side. The r vector is there. R sine theta is a, the perpendicular distance between. As the particle moves along and r follows it, r sine theta is a quantity that never changes. R sine theta is the perpendicular distance between the two lines that I drew, and at no point does that change. Which means that since the mass is a constant and the velocity is a constant because it's moving along with constant speed, therefore constant momentum, and A is a constant, this angular momentum for the diagram that I've drawn is a constant quantity. It does not change. It is conserved. And that makes sense because this particle doesn't have any forces acting on it at all. It's a free particle. It has no forces acting on it at all. And since there are no forces, then there's no change in momentum. But particular to what I'm talking about now, since there are no forces acting on it, there are no torques. And in the case where the torque is zero, the angular momentum does not change. So the particle moves along with constant angular momentum. It's curious though, isn't it? Why does a particle traveling in a straight line have angular momentum? Well, the only answer that I have to that is by definition. It's a little funny though, because imagine that I had decided to have the particle, instead of going along this line that is parallel to the x-axis, that instead I had it go along the x-axis such that when it was over here on the left, it was heading directly towards the origin of my coordinate system, the axis of rotation that I've chosen. It's heading directly toward that. Its angular momentum would be zero because the impact parameter is zero. And as it passed through that point and continued on to the right here, still going to be zero because the angle between the angular momentum and between the momentum and the position vector would be 180 degrees. Still zero. And so its angular momentum would be zero the whole time. So in this sense, the angular momentum of the particle coming in is arbitrary, like gravitational potential energy. It's not the value of the quantity that matters. What matters is the change in the quantity. And changes of angular momentum are really, really important, the way they affect the behavior of physical systems.
If you were to get a problem that just had like the x and then the object with the vector,
Yeah.
and you chose to draw the parallel lines to like create the planes like vertically,
Mm-hmm.
would it still be correct? Like the same?
Yeah, so it's an important question. One thing I want to impress upon you before I answer that question is this thing that I've drawn here is so silly and simple that it will never be an issue in problem solving. I'm doing this for the definition. But the point you make is valid. This is what I mean when I say the choice is arbitrary. I cannot choose wrongly here. Wherever I put the axis in whatever direction I draw them, as long as I respect the cross product by definition, the diagram and where I choose the axis to be is irrelevant, and yes, it will all work itself out. Just like I could solve a projectile motion problem launched from up here on a cliff and hits down here. I could put the origin of the coordinate system in Paris. It still works out because it's independent of coordinate system. The same principle is at work here. It doesn't matter about the coordinate system. Now,
It works in the y direction too.
sure, yeah, doesn't matter. Independent of coordinate system. Now, I still have not appreciated the fact that the angular momentum is a vector quantity. So let me now address that. The vectorness of the angular momentum comes from the cross product. The cross product is the vector product. The result of a cross product between two vectors is a vector. So all I have to do is to figure out what the result of the cross product would be, and for that I need my right hand. Because the vector result of a vector cross product comes from the right-hand rule. The right-hand rule, which we've already encountered for torque but found it less useful, is to point my fingers of my right hand in the direction of the first vector, which here is the radius vector, and then curl them in the direction of the second vector, which is the momentum vector. So I'll take the fingers of my right hand and curl them in the direction of the momentum, and I'll find that in this case my thumb points into the board. And so the angular momentum vector points into the board. That is useful to know. That is useful to know. I'll reiterate as an aside that when I calculate a torque, it's R cross the force. And when I do that cross product, my thumb points in the direction of the change in the angular momentum vector. But here, R cross P, apply the right-hand rule, and my thumb points in the direction of the angular momentum vector. If the particle were traveling from right to left, instead of left to right, the angular momentum vector would point out of the board. This is important to me because angular momentum is a conserved quantity. It's okay, though, to dial back to the beginning and say that angular momentum is a moment of inertia multiplied by an angular speed, I omega. That's the magnitude of the moment of inertia, or magnitude of the angular momentum, pardon me. This wheel here, this bike wheel, with two handles on the end of it, it has a moment of inertia, certainly, because it has mass distributed in space. And I can quite easily give it an angular velocity. Now, it has a moment of inertia and it has an angular velocity, and so it has an angular momentum. What is the direction of the angular momentum vector? Oh, goodness. I can clearly see it in the context of a single particle, but now I have this massive rotating object, and I want to determine what is the direction of its angular momentum. How shall I do that? Well, imagine one particle of it, right? One particle right here on the edge. Now, I can't freeze time, at least not in public, because then it just, people would go nuts. So, one particle right there, right? Don't follow it. Right here. The radius vector points from the axle here, radially outward to the left. And there's a particle there that has a velocity downward, and so therefore a momentum downward. So, fingers, right hand, fingers in the direction of the radius, curl in the direction of the velocity, which is downward, and that's thus the momentum downward. And my thumb points in the direction of the angular momentum, and immediately I discover something very convenient. If you want to know the direction of the angular momentum vector of this wheel, just curl the fingers of your right hand in the direction that it's rotating. How's that for convenient? Just curl the fingers of your right hand in the direction that it's rotating, and your thumb points in the direction of the angular momentum. The angular momentum vector points straight out from the axle here. It's pointing straight at you. And that angular momentum is a conserved quantity, which is why this happens. Magic! No, it's not magic. Riding a bicycle does not require balance because the bicycle wheel has angular momentum, and a bicycle wheel doesn't want to fall over because the angular momentum vector is conserved. No, Shadi, it's not conserved. The angular momentum vector points out from the axle, yes, but it's going around like a lighthouse when you do that. It's going around like a lighthouse. That's not conserved. The angular momentum vector is changing. Well, what's the condition for the angular momentum to be ultimately conserved? No external torques. Is there an external torque acting on this wheel? If the axis of rotation is one end? Is there an external torque acting on the wheel? An outside agent exerting a force on the center of mass of the wheel that exerts a torque? Jules, please tell me.
Yes.
And what force is that?
Your hand pulling it.
No, my hand is acting at the axis of rotation, so it doesn't exert a torque. Yeah, see how easy it was that we forgot gravity for a second. The external gravitational force exerts a torque, which changes the angular momentum, right? But the reason why it stands up like that, so if we want to see a case, I have to show you a case where gravity does not exert a torque, right? So I have to orient it in such a way, I have to orient it in such a way so that gravity acts through the axis of rotation. The angular momentum vector in this case points straight upward, and Shadi, it's starting to process like a top does. Why is the procession happening? Because of imperfections. I can't hold it perfectly vertically. Perfectly vertically is an unstable equilibrium for this thing. Early in my career, I used to, at this point, take my wallet out of my pocket and place my wallet over my eye socket and then put the wheel, I stopped doing that one horrible day when I almost poked my eye out. So, the things you do for physics. What I should do is like 3D print some sort of fixture that goes on there, right? Scan my skull and make a special eye patch that I can wear. I have all sorts of concerned looks right now, right? So I think you know what comes next. What comes next is I have to ask the question, which of the Clancy sisters is the stronger? Oh, yeah? You have been. She sure did. Sure did. Now, the reason why. The reason why.